Good afternoon, Southminster scholars. A final reminder to you about the Superheroes Fund. Thank you again on behalf of the committee for all of you who have contributed to that fund. It is so meaningful, not only to us, but to the hourly paid workers. If you've not yet done so, please do so by the end of November, which is our final time to complete the fund. Today we're going to study comets, interplanetary nomads. Comets appear in the skies at random times. Some are predictable. What are the details of their long tails, their nucleus? How big are they? Or how icy are they? How are comets classified? How do they create showers? Some comets have crashed into planets. Halley's Comet regularly appears every 76 years. What do solar winds have to do with comets? Dr. Summers will describe Halley's Comet today, but also teach us about comets in general. I hope you enjoy.
Throughout history, the irregular appearances of comets have been considered both an omen and a puzzle. A puzzle because comets seem to not follow the rules. Their arrivals couldn't be predicted, and they did not follow the regular motions. They grew in brightness and faded in brightness, and sometimes they even outshone the planets. They developed long tails and could dominate the night sky. Their unpredictability provoked fear. Hence, comets must be omens. Surely the appearance of a new celestial object must have great meaning for the affairs of men. These meanings were generally taken as portents of doom. A Chinese text describes the meanings of the shapes of comet tails. One represented civil war, one foretold of revolt in the army, and another showed that there would be a death of a king. That last example was also found woven into the Bayeux Tapestry. And in this image, you can see appearance of a comet in the upper left. It turns out this was Halley's Comet appearing in 1066. It made a very striking appearance in Earth's skies around the time that William the Conqueror invaded England. As depicted here in the tapestry, it was deemed a bad omen for King Harold of England. And in fact, he actually died later that year. A 1665 book was even more rabble-rousing about the effect of comets. Threatening the world with famine, plague, and war, to princes death, to kingdoms many crosses, to all estates inevitable losses, to herdsmen rot, to plowmen hapless seasons, to sailors storms, to cities civil treasons. That's a quote from De Comets by John Gadbury, published in London 1665. So there has been a lot of historical hysteria about comets, and it's sort of nice to think that, oh, that happened only in the past. But when Halley's Comet passed by in 1910, the media learned that the Earth would be passing through its tail, and that its tail contained the poisonous gas cyanogen. This caused quite a bit of panic, including this book here, which predicted the end of the world. Fortunately, that didn't happen. Now, more rational thought and order in the solar system can be restored by making comets predictable. This is what Edmund Halley did in the mid-1700s. He noted that the comets of 1531, 1607, and 1682 had similar orbital elements, and he postulated that they were in fact the same comet. Therefore, he was able to predict the return in 1758 and 1759. The comet was then named after him, and it's given the scientific designation 1P/Halley, where 1P indicates that it's the first periodic comet. It's given Halley, and you'll note that the comets are one of the few things where the discoverer's name is actually attached to it. Using historical and Chinese observations, we are able to go back about 30 orbits to see return of Halley's Comet all the way back to about 240 BCE. And that's how we know that the 1066 comet was an appearance of Halley. This predictability then becomes power. Here is the orbit of Halley's Comet, and as you can see, it comes into the inner solar system, and it goes all the way out past the orbit of Neptune. As we mentioned in a previous lecture, it returned 1 day late in 1835. Because this orbit samples the gravity of the outer solar system, this helped convince astronomers that the problems that they saw in Uranus's orbit at the time might be due to an unknown planet. It turns out that comets really can serve as scientific omens. Let's look in detail at the structure of a comet. This is an image of comet Hyakutake, and the visible parts of the comet are shown quite well in this image. The head of it, which is called the coma, and this big long tail that is streaming away. Now, neither of these parts really are the comet itself. The comet is really contained in a nucleus that's deep inside the coma, and it's rarely seen. Our observations and our understanding of comet nuclei are, well, I'd say they're perhaps a little bit skewed, because we observe mostly the bright comets, like Comet Halley, or the recent comets, like Comet Hale-Bopp, or the comets visited by spacecraft, like Tempel 1 and Wild 2. This is the image from the Stardust satellite of Comet Wild 2. This is the nucleus of Comet Wild 2, and you'll note that it has a very asteroid-like appearance. It's irregularly shaped, and it has a rather pockmarked surface. It's also rather tiny. It's only about 5 kilometers across. Now, the general idea and how we think of these comet nuclei is what we call the dirty snowball model. Their sizes are from about 1 to 10 kilometers, although I'll note that Hale-Bopp was especially large. We found that that one was about 40 kilometers in size. Now, these are about the size of sort of the smallest moons that we discussed in the moon lecture, and certainly some moons are in fact captured comets. The surface, although it appears bright here, is actually composed of very dark material. It's always described as blacker than coal. It's not ice, but it's rather carbon-rich encrusted materials. Basically, it's similar to the ring particles of Jupiter, Uranus, and Neptune, where there probably was ice on the surface, but the particle bombardment, in this case from the solar wind, has gotten rid of the ice and left the carbon-rich material, which makes the surface black. Now, the temperature of this surface will vary depending upon where it is in its orbit. Certainly, when it's way out away from the sun, it's going to be very cold. The temperatures in the outer solar system are around 200 degrees below zero. But it can also be very hot. Comet Halley, when measured when it was just inside the Earth's orbit radius at 0.8 of an astronomical unit, was measured to be 57 degrees Celsius. That's 135 degrees Fahrenheit, and really the same as the highest temperature ever recorded in Death Valley. Basically, Halley, when it was inside the orbit of the sun, was hot asphalt baking in the sun's light. The interior composition of these comet nuclei is thought to be mostly ices. And the gas around Comet Halley, if it sort of fits what the interior is like, it was 80% water ice, 10% carbon monoxide, and 3.5% carbon dioxide. We have, however, looked inside one comet. We only sampled the gas around Comet Halley, but we were actually able to look at the inside of Comet Tempel 1. And we did so with a mission called Deep Impact. Here is the nucleus of Comet Tempel 1 as seen by Deep Impact. It's about 8 kilometers by 5 kilometers across. And the Deep Impact mission flew by Tempel 1, and as it was flying by, it released a probe, and it sent that probe to crash into the comet so that ejecta would be spewed out, and we could examine the ejecta to explore the interior of the comet. As I described it at the time, it was basically a washing machine slamming into an iceberg at 25,000 miles per hour. So, what happened? Well, this is the image here from the impactor about 5 minutes before impact. Here's the image 90 seconds to impact, and here is 60 seconds to impact. You can see that they have craters here, and this crater just below center is about half a kilometer across. The impactor hit just above this crater. If we watch from the flyby spacecraft, here you can see just as it hit, and a big bright flash, you can see the impact. If we step forward in the imageries, you can see here that there is a large plume of material that was immediately sent out, poof, away from the comet nucleus. This indicates that it has a crusty surface with a low-density interior. If it had a much harder surface, the material wouldn't have pushed back so quickly. As we follow through the impact, that material sprays off, and then material from the inside starts to spray out. And here you can see the plume of material starting to come out from the comet. This is what we saw from the flyby spacecraft. But many telescopes watched the impact, including the Hubble Space Telescope. And we have 3 images here from the Hubble Space Telescope. The one on the left is 1 minute before the impact. The one on the center is 9 minutes after the impact, and even from Earth, we can see that the impact has caused a considerable brightening of the comet. And then finally, 1.5 hours after impact, you can see just how far this gigantic spray of material went out into space. So we studied this material with many different telescopes to see what it was composed of to try and understand the interior of the comets. And the results were that it was a very porous composition. They described it as being like a snowbank, and that there was no indication of solid ice. The material was also finer than expected. It had the consistency of talcum powder when they expected it to have the consistency of sand. There was a little less water ice than expected, and water ice was still the dominant material, but they also saw more dust than they had expected. Overall, it was rather a puzzling mix of materials, because the ices form where it's cold. They saw some materials called crystalline silicates that have to form at high temperature about 1,000 degrees. They also saw some clays and some carbonates that need liquid water in which to form. So you've got cold stuff, you've got hot stuff, and you've got aqueous stuff, water, needing water stuff, all within the same comet nucleus. So the comet interior composition was not indicative of any one location, and it rather confuses the picture of their origins. Now there's another major feature of the comet nucleus. Here is a picture of Comet Halley taken by the spacecraft Giotto, and what you see in this image are the jets coming off the comet nucleus. These are created by the sublimation of the ices, where ice goes directly from solid to gaseous. There's very little ice on the surface of these comets, but the comets have very porous surface and a very hot surface, so the heat as it diffuses into the interior of the comet causes the ice to sublimate and shoot out through the very porous surface as these jets. These ices also carry away dust particles, and the gas and the dust flows away from the comet nucleus. This is what forms the coma. Here's an image of Comet Neat, and you can see it's got a wonderful coma here, and you can see the tail going past. This coma, this bright coma, you can see you can sort of think you see the nucleus in there. No, it's much too small to see here. This coma is created from these gas and dust spewed off by the nucleus, and this coma is about 1 million kilometers across. Now, I said the nucleus was only a few kilometers across, so that's much bigger. So even that bright dot there can't actually be the nucleus. It's much too small to see. The coma develops when the comet gets within about 3 astronomical units of the Sun, or 3 times the Earth-Sun distance. Once the Sun heats its surface enough, the interior water ice will sublimate, spew out, and create the coma. The gases given off by the nucleus are broken down by sunlight. And so the composition of the coma changes with distance from the nucleus. The further you are from the nucleus, the more it is unlike the interior composition of the comet. We flew through the coma of a comet with a mission called Stardust and collected samples. Here is a picture of the return capsule. What we did with, if you see in the lower right, you see the guy in the bunny suit holding onto the sample grid. Basically, we flew past Comet Wild 2 through its coma. We opened up, and in this grid here, there's a substance called aerogel, and the aerogel caught the particles from the comet. Then the mission came back to Earth, and the return capsule you see here on the left came down to Earth, landed in the desert, and we were able to actually study the particles from the comet here on Earth. The results in the laboratory have been actually even similar to the Deep Impact mission. We found ices that form in the cold region, and they are mixed with materials that should only form in the hot regions. And so together, from Deep Impact and Stardust, they sort of confirm that we're a little confused about comet origins. Now, the outer boundary of the coma is defined by the interaction with the solar wind. Now, the evidence of the interaction with the solar wind can be seen in X-ray observations. Here is a picture from the X-ray satellite ROSAT of comet Hyakutake. And you can see that there are X-rays on the sunward side of the comet, and it's not in the direction of the comet motion, that the particles are hitting from the sunward side. And it's very surprising just how strong you get X-ray emission from a comet, because we don't think of comets as being high-energy objects. Why would we be getting X-rays from it? Well, it just says that the particles of the solar wind are really smashing into the coma and creating this X-ray emission. The solar wind then pushes the coma particles away, and that forms the comet's tail. Here is an image of comet Ikeya-Seki, and it was observed in 1966. So if the coma can be on order 100,000 or 1,000,000 kilometers across, take a look at this very long tail, and you can see that it can stretch for tens of millions of kilometers. Because they are pushed back by the solar wind, the tails always point away from the sun. Here is a movie that shows you a bit of that. This is Comet Neat passing by the sun as observed by the SOHO spacecraft. The comet will come in from the top and swing past it and head out in the lower right. So you can see the tail pushing away from the sun, being pushed back by the solar wind. Now, comets don't have just one tail. They have both gas and dust emitted by the nucleus, and gas and dust each form a separate tail. This is an absolutely spectacular image of Comet McNaught. Matter of fact, it's an image taken by McNaught himself, the man who discovered the comet, about 6 months before this image was taken. It shows you an incredible panoply of the dust tail, which appears yellowish because it's colored by reflected sunlight. It is a very curved tail, and the dust is following the orbital trajectories as it's pushed away by the solar radiation. This image here was taken about 1 week after Comet McNaught passed by the sun, and you can really see the motion of the comet in its orbit and how the tail sweeps through the sky, because you're seeing the tail as it was released over the course of that week or so. Now, the other tail is called the ion tail, and you can see both tails in this image of Comet Hale-Bopp. The dust tail is here on the top, and that's the more yellow tail stretching up. The blue tail is the ion or plasma tail. It appears blue because of the fluorescence of carbon monoxide molecules. The gas particles in the coma have been ionized as they're getting hit by the solar wind, And instead of being pushed away by the radiation, they're actually carried away by the magnetic field lines of the solar wind. Hence, you get a straighter tail for the magnetic field pushing these ions out away from the sun. Also, because the magnetic field moves a little bit faster, the ion tail can be up to 10 times longer than the dust tail. The ion tail is also affected by changes in the sun's magnetic field, and it can break up in what we call a disconnection event. This is where part of the ion tail detaches and then reforms. In this image, you can see that at the top, the ion tail is intact. And then in the second image, you can start to see a break forming in it. And by the third image, we have the disconnection event that is pushing off, and slowly that disconnected part will flow away and the ion tail will reform and become its long self. This occurs when the comet crosses a sector boundary of the magnetic field, basically a change in the polarity of the solar wind's magnetic field. Now, there's a spectacular disconnection event seen in a movie. And this movie is of Comet Encke, and it was hit by a coronal mass ejection. The comet starts as this little dot here on the left of the screen, and all this emission on the right of the screen are the emissions from the sun. And so if I start it up, you can see the comet approaching, and then this big coronal mass ejection sweeps through, causes a disconnection event, and then you also see the strong interaction of the solar wind and the comet's tail as it comes through. Well, that's the structure of a comet. Now, let's take a look at their orbits. We have the short period comets that take up to 200 years to orbit the sun. And here is a diagram of most of the short period comets. You can see the orbits are confined mostly to the interior of Jupiter's orbit. They can have any orbit shape. They can be really elongated or nearly circular. If we look into the central region, you can see, just barely pick out here, there's Mercury's orbit, Venus's orbit, and Earth's orbit, and I can hardly even see Mars's orbit. But you can see that many of these comets pass near or cross through Earth's orbit. These are the comets that we see on a regular basis. Now, most of them are not that bright, so they're not the spectacular comets like the Hale-Bops, but there are many comets that pass through the inner solar system on a regular basis. And if we look at this edge on to the solar system, you can see that most of the comet orbits are in the ecliptic plane. There are only a handful of deviations, and you can see that those are really those that have the longer periods. On the contrast to the short period comets, we also have the long period comets. These are comets that have orbital periods greater than 200 years, and they can actually be tens of thousands of years long. Originally, it was thought that these comets were hyperbolic, that they came from interstellar space, they swooped through the solar system, and they never returned. Well, we know that's not true. We now know them to be very elongated ellipses. So here are just a few of the long period comets, and you can see that they extend well beyond the planet's orbits. I've included Comet Halley over here in the upper left around 10 o'clock just for scale. And you can see Halley goes out to Neptune. All of these comets go well, well beyond Neptune. If you look at this edge on, you can see that none of them are in the plane of the ecliptic. And they extend very far out. This is the orbits of the planets. They can extend much further out to hundreds of AU and even out to thousands of astronomical units. But still, they are gravitationally bound to the sun. If one looks at the full distribution of orbits, you find that most have very, very long periods, and essentially, they have random orientations. In the ones that I picked out here, they all seem to be below the plane. Many of them are, in fact, above the plane. They're actually at all orientations around the solar system. So most long-period comets are seen once and never seen again, because they take tens of thousands of years in their orbits, while the short-period comets are seen over and over until they are destroyed. Because the short-period comets can't last for that long, or at least compared to the age of the solar system. If you go past the sun, you're going to lose 0.1 to 1% of your mass each perihelion passage. Each time you go past the sun, you're going to lose a bit of your mass. That limits comets to about a few hundred or maybe a few thousand orbits that go close into the sun. Now, the evidence for this kind of mass loss can be seen in the night sky. It can be seen in images like this. This is an image of a meteor shower, and these are pieces of comets raining down on Earth. You see, the material that's ejected from the comet gets strewn out along the comet's orbit. And as Earth passes through the orbit of a comet, that's when you get a meteor shower. And these showers are actually associated with specific comets. One of the brightest showers of the year is called the Perseids, and that's associated with Comet Swift-Tuttle. The Leonids with Comet Tempel-Tuttle, and the Ursids with just Comet Tuttle. So you can see this guy Tuttle spent a lot of time finding comets. Comet Halley is actually associated with two meteor showers, the Orionids and the Eta Aquarids. Now, these showers can have a few meteors, or they can have many meteors, and that really depends on how recently the comet passed through the inner solar system, just how much stuff has recently been strewn out into that part of the orbit that we're passing through. Comets give off just a little bit of stuff in normal times, but sometimes they've been observed to entirely break apart. This is an image of Comet 73P Schwarzmann-Wachmann 3. It was observed to break into several large pieces. The ones in this image are labeled B, G, R, and N. Now, originally, they were labeled with consecutive letters, but some of the pieces disappeared between the orbit when it broke apart and the orbit when it's being observed here. The pieces themselves also released many fragments, and we looked at fragments B and G with the Hubble Space Telescope, and here you can see that there is a main part to these fragments B and G, but there are also many, many small fragments released off of these. And this caused the Schwarzmann-Wachmann 3 to brighten because the many, many particles reflected a lot more sunlight than just the one comet nucleus would have. So the remains of Schwarzmann-Wachmann 3 may not have many more orbits left before it breaks apart or crashes into the sun or otherwise disappears. We have actually seen one comet suffered a catastrophic breakup, and this is the comet Shoemaker-Levy 9. Here is an image of the breakup of Shoemaker-Levy 9 after its breakup. Matter of fact, we didn't observe it before its breakup. It broke into many pieces and was disrupted by Jupiter's gravity. We only observed it after it had been captured by Jupiter's gravity and had already broken into these pieces. Eventually, Shoemaker-Levy 9 crashed into Jupiter, and it was a spectacular death of a comet. So these breakups indicate that the comet interior is not strongly held together. One thinks of the comet interiors as, are they monolithic? Is it all one great big snowball? Or is it a compendium of packed together, many snowballs packed together? And these breakups indicate that it's probably the latter view. Now, like Icarus, comets can get into trouble if they pass too close to the sun. This movie here shows two comets that swing close to the sun, and they're being observed by the SOHO satellite, but they never were observed to travel away. They're going to appear in the lower left here and swing up towards the sun. So here come the comets, and they swoop in, and then the sun has a coronal mass ejection, as if it swallowed up those comets and it's burping afterwards. Now, the SOHO satellite has been prolific at finding comets. It has observed over 1,000 comets, many of them sun grazers like this, many of them that did not swoop out the other side, and we presume were destroyed in their passage by the sun. So comets have been observed to die, and new comets have appeared in our sky. This cycle of destruction of comets and appearance of new comets indicates that we must have some resupply reservoir for comets. And that's what we'll get to in our next lecture. We will discuss the two reservoirs, one for the short period comets and one for the long period comets. And in doing so, we'll explore a brand new region of the solar system, one that had not been observed until the last 2 decades. We'll see you then. Take care.